The maximum entropy principle.
So some important notes. The log base 2 of x is the natural log of x over the natural log of 2, and the natural log of x is therefore the natural log of 2 times the log base 2 of x. If we use the natural log of x, then we're using nats instead of bits. One nat is about 1.44 bits. Also, self-information, sometimes I use capital Y of x, but we're trying to use consistently the notation little h of x for self-information. So entropy is the expected value of h of x.
So let's review. Suppose we have a joint probability distribution. Then we get joint surprisal from x being t sub x and y being u sub y in the same trial. It's the negative base 2 logarithm of p of xy in bits, or the negative natural log of p of xy in nats. So h of x is the surprisal from x equals t sub x, h of y surprisal from y equals u sub y. If x is independent of y, then the self-information joint is equal to the sum of the individual self-informations. The entropy for a joint distribution is the expected value of the joint surprisal, which is going to be a double sum over x and y of the joint distribution times the base 2 logarithm of p of xy, and of course it's negative. And it's only over those distribution values which are greater than 0. Probability equals 0 doesn't contribute to entropy. So the entropy of the variable x is the expected value of h of x. The entropy of the variable y is the expected value of h of y. The joint entropy is the expected value of the joint surprisal, which if they're independent, then it's equal to the expected value of the sum, which is the sum of the expected values, which means we have the sum of the entropies. In other words, if x is independent of y, then the joint entropy is the sum of the individual entropies. So entropy can be thought of as a function on probability distributions. Let me explain. Here's Shannon entropy, and we can think of it as a function of variables P1 to Pr with the constraints that the P's are non-negative and sum to 1. For example, a binary classifier would have a P1 and a P2. The entropy would be h of P1 and P2, which is negative P1 log base 2 P1 minus P2 log base 2 of P2. The constraint, P1 plus P2 equals 1, means that P2 is 1 minus P1. Just relabel the P1 by just P. And then our entropy, h of P is negative P log base 2 of P minus 1 minus P log base 2 of 1 minus P. That is, entropy is actually a function of r minus 1 variables because we can eliminate one using the fact that they sum to 1. Notice that self-information is non-negative, so entropy is non-negative. And what if we had p sub I as 1 for some I, which would have to force all the other p's to be 0? Well, then our entropy would be 0. And as p sub I decreases from 1, the surprisal increases. So entropy is a measure of disorder. If an event always occurs, its entropy is 0. But if that event becomes more uncertain, its entropy is positive and increases with the event's uncertainty. Well, that's intuitively, but we can only go so far with intuition. Let's look at the math. The math is convexity. Now, remember that a set C, a subset of Rn, is convex if 2 points P, Q in C implies that the line segment between them, 1 minus alpha P plus alpha Q, is also in C, where alpha is in 0, 1. A function is convex if its epigraph is convex, and its epigraph is a set of points in Rn plus 1 for which the function f of x is less than or equal to y. That is, f is convex if its graph and the region above it form a set that contains all the line segments between its points. In other words, if the epigraph is convex, if you've got 2 points PQ, Then the line segment between them is also in there, where this 1 minus alpha p plus alpha q is just the notation for all the points on the line segment between p and q. Alpha equals 0 is p, alpha equals 1 is q. So if I let x alpha be 1 minus alpha x naught plus alpha x1 for x naught and x1 in C, and y alpha be 1 minus alpha f of x naught plus alpha f of x1, then it's a nice little exercise to show that the point x alpha comma y alpha is in the epigraph. Here's a hint on how to do so. And since f of x alpha is less than or equal to y alpha, if f is convex, then we have this new definition for what it means for a function to be convex.
So function f from R into R is convex if for x0, x1, and Rn, alpha in the closed interval 0, 1, f of 1 minus alpha x naught plus alpha of x1, that quantity, is less than or equal to 1 minus alpha f of x naught plus alpha f of x1. We often restate this in zeroth order conditions. P0 is 1 minus alpha, P1 is alpha. Notice now the P0, P1 sums to 1 and are non-negative. F of P0 x0 plus P1 x1 is less than or equal to P0 f of x0 plus P1 f of x1. And notice what we've done is we've begun using probability distributions. First order conditions is that the y equals f of x is always above its tangents. In other words, f of x is greater than or equal to LP of x for all x, p, and Rn, where LP of x is the tangent. The definition of LP of x gives us our first order condition, f of x greater than or equal to f of p plus the gradient of f p transpose x minus p, where the gradient is the column vector of partial derivatives, and for one variable it's just the derivative. Let me show you that first order implies convexity because it shows you how we work with convexity. If x alpha is 1 minus alpha x naught plus alpha x1, then simple calculations give us these two, which we'll use in a minute. Now, first order centered at p equals x alpha for x naught looks like this. At p equals x alpha with x1 looks like this. Multiply the top by 1 minus alpha, the bottom by alpha, and then use our conditions above. And now let's combine these. In the beginning, we get the 1 minus alpha f of x naught plus alpha x f of x1 greater than or equal to f of x alpha. But notice that the switching of the signs, x naught minus x1, x1 minus x naught, means that the last two terms cancel. And that's our proof. Now this leads to an important general form. A function is convex if and only if f of p1 x1 all the way up to pr xr is less than or equal to p1 f of x1 plus p2 f of x2 all the way up to pr f of xr for all probability distributions on R objects. The proof's by induction. We assume it's true up to r minus 1 and that pr is not equal to 1. And then we let q sub I be p sub I over 1 minus p sub r. Then the q1 to qr minus 1 adds to 1 and are non-negative. And if we use convexity, our definition, we end up with this expression. And notice that by the induction hypothesis we get this. And then we multiply through by the 1 minus PR and use our definition of the Q's. And we end up with our conclusion. So in summation notation, we write the theorem in this form. And notice if we let R equals 2, we get the previous slide that the epigraph is convex. So the math is convexity. Our theorems establish that in general, a convex function satisfies this, which is actually known as Jensen's inequality. Notice that this expected value is a convex linear combination. Also notice if negative of a function is convex, then the function itself will be said to be concave. And this is going to be very important for us moving forward. Another theorem is that if we have f sub j's, r into r, are convex functions for all j equals 1 to m, then any convex combination of the f sub j's is also convex. It's a good exercise, like maybe on a midterm or final. So let's look at what happens if we restrict to functions of one variable, f, some subset of r to r. It's convex on this subset if we get Jensen's inequality. Convex means curving up with respect to the horizontal. Concave means curving down with respect to the horizontal. If r equals 2, then Jensen's inequality gives me our 0th order condition. If I've got a convex function, then I've got f of x1 and f of x2 at points x1 and x2. I draw this secant line. I look at the convex combination of the x's, and that function value is below the secant line value. That's the 0th order condition. And remember also, if f is differentiable, then y equals f of x is above each of its tangent lines.
So if f is continuous and convex on AB, then it actually has a unique minimum. So min here stands for minimum. We can see the minimum here is at A, and A is called the argmin of f. So here we also have a minimum, but it's at some C, which is the argmin of f. And notice that the gradient of f at C is equal to 0. And the gradient's what we usually call the derivative. So here's another example of a minimum, but in this case the argmin is an entire interval. And here the argmin is also an entire interval. So there are theorems and proofs which you could learn in a course on convex optimization. We're not going to look at them here except for one very important theorem we look at next.
So our theorem is that if f prime is continuous and increasing on an open interval in R, then f is convex on that open interval. The proof, let x1 be less than x2 in AB. Continuity gives us the mean value theorem, which says there exists C in x1, x2 such that the secant slope is equal to f prime of C. Let's move the x2 minus x1 over here. And now we're going to use the fact that the f prime is increasing. C is bigger than x1, so f prime of C is bigger than f prime of x1. But then if we add the f of x1 to both sides, we get our first order convexity. Now, notice this only required f prime be non-decreasing. And also, f prime increasing implies that the second derivative is greater than 0, the second derivative test. Because entropy is a concave function. So here's my Shannon entropy. If I take the derivative of p log base 2 of pi, and notice we often use partial derivative when we have more than one variable, but notice this derivative is increasing. Therefore, this p sub I log base 2 of p sub I is convex. This is a convex combination, and then the negative makes it concave. So convexity means we have a global minimum. Concavity means we must have a global maximum. The global max, in fact, is the uniform distribution. So remember that if all these u's are equal to 1 over r, then our entropy is the log base 2 of r. And the entropy of any other probability distribution is less than or equal to the entropy for the uniform distribution. Systems tend to increase in entropy or move toward disorder. This gives us the maximum entropy principle. The best model is the one that allows the most uncertainty from the data. See, knowledge is information or constraints on a process. Systems maximize disorder within their constraints. The best model should therefore assign an unbiased probability to every event not excluded by the given information. Intuitively, anything we can explain or constrain is allowed to have as much uncertainty as possible.
So let's look at, for example, at two outcomes, which would have a probability of p or 1 minus p. The entropy is a function of p, and as a function of p, it reaches a maximum when p is equal to a half. Therefore, a fair coin is the most random or has the maximum entropy process with two outcomes.
There are always constraints. Constraints or equations, inequalities, or other conditions on the variables in the entropy. For example, the variables are constrained to sum to 1. Also, they're constrained to be greater than 0, but we typically don't use these as constraints for reasons we'll see later. Constraints are equations of the form c sub j of the variables equals 0. And that's going to lead us to define a new function called the Lagrangian, which we'll look at more closely in the next video. Or we'll substitute our constraint equations into H, which is what we're going to do in this video.
So suppose the process has 3 outcomes, red, green, and blue. So we'll let P be the probability of red, Q be the probability of green, but notice the probability of blue is 1 minus P minus Q because the 3 probabilities sum to 1. So this is our entropy. So let's notice that as a surface, we can definitely see a maximum, and it occurs at 1/3, 1/3, which is, if you remember, 1 minus P minus Q is the other probability, which is also 1/3. So if we don't know anything, and there are 3 possible outcomes, then the least bias, the one that allows the most uncertainty, is a probability of 1/3 for each of the outcomes. But suppose we know that the probability of green is 1/2. In other words, Q is equal to 1/2. If nothing else is known, then we would assume that the least biased, the maximum entropy model, assigns probability of 1/4 to the other 2 outcomes. And this is in fact the model we get from the maximum entropy principle, as we'll now see. So suppose it is known that the probability of green is 1/2. In other words, Q is equal to 1/2. Our entropy, with Q equals 1/2 substituted, is given by this, where instead of 1 minus Q minus P, we now have 1/2 minus P. The derivative, recall definition of arbitrary logarithms, and the derivative of log is 1 over P, the natural log. And here's our derivative using the product rule. Notice we can cancel the P's, cancel the 1/2 minus P's. We get a minus 1 over log 2 plus 1 over log 2 that cancels and gives us our derivative is negative log base 2 of P plus log base 2 of 1/2 minus P. The derivative is 0 when log base 2 of P is equal to log base 2 of 1/2 minus P, or when P is equal to 1/2 minus P, which is 2P equals 1/2, which is P equal to 1/4. So maximum entropy model means maximum uncertainty for those parts of the process which are unknown. The entropy, for example, was maximized at P equals 1/4 in this example. If it's known that P probability of green is 1/2, and that's all we know, then the unknown should be as uncertain as possible, which means the probability of red, the probability of blue is 1/4. This has important consequences. Many of our models will be developed using entropy. Entropy can be used to classify patterns. It can even tell us when there are no patterns. Maximum entropy is going to give us our best probability distribution. And we'll obtain best probability distributions via information, not randomness, implying that a probability is probably better thought of as a Bayesian belief or confidence. And in fact, any number between 0 and 1 that we encounter, we're likely going to call it a probability, even if it's a proportion or a relative frequency. But even when using the, quote, concept of probability, just keep in mind our true goal in context is information.